Good morning. Today we are going to review electric potential for AP Physics C, Electricity and Magnetism.
Flippin' Physics!
Where we start is actually by pointing out that the electrostatic force is a conservative force. When I say that, Bobby, what equation should immediately leap into your brain?
What equation leaps into my brain when you say the electrostatic force is a conservative force?
Exactly.
I do not know.
The equation is the force in the x direction equals the negative of the derivative with respect to x position of the potential energy associated with that force.
Right. That means the electrostatic force equals the negative of the derivative of electric potential energy with respect to position.
Thank you, Bobby and Bo. Let's use the more general R variable to identify it could be any direction. We can rearrange that equation, and because it has to be the force in the direction we are taking the derivative, this is actually the dot product of the force and the infinitesimally small change in position dr. Take the integral of both sides, and we get that the change in electric potential energy of an object equals the negative of the integral of the dot product of electrostatic force acting on the object and the infinitesimally small displacement dr. Billy, please give us the equation which relates the electric field to the electrostatic force and use that to further determine the equation for change in electric potential energy of a charge.
The electric field equals the electric force divided by charge. That means the electric force equals the charge times the electric field. We can substitute that back into the electric potential energy equation. We can assume the charge in the electric field is constant, so we can take charge out from under the integral. And we can have either the dot product version of the equation or the one without vectors and the cosine of the angle between the direction of the electric field and displacement dr instead of vectors.
Well done, Billy. We've now determined the change in electric potential energy experienced by a charged particle which has moved from point A to point B in an electric field. Notice, because the electrostatic force is a conservative force, this change in electric potential energy does not depend on the path taken from point A to point B. To make a comparison to gravitational potential energy, if we lift an object vertically upward in a constant downward gravitational field, it will experience a positive change in gravitational potential energy. In other words, I have increased the gravitational potential energy of this mass. Bo, what happens if I let go of the mass?
It goes downward.
It accelerates downward.
It accelerates in the direction of the gravitational field.
Sure.
Right. Conservation of energy says that gravitational potential energy of the mass will decrease and the kinetic energy of the mass will increase. And if we change the gravitational field to an electric field and use a positively charged object instead, notice that when we move the positively charged object opposite the direction of the electric field, it will gain electric potential energy just like the mass did when I lifted it. And Bo, what happens if I let go of the positive charge?
It goes downward.
It accelerates downward.
It accelerates in the direction of the electric field.
Sure. As the electric potential energy of the positive charge decreases, it gains kinetic energy.
Exactly. Now, if I change the charge
If I change the charge to a negative charge, as I move the negative charge, this time in the direction of the electric field, Bo, what happens to the electric potential energy of the charge now?
Well, it actually increases, right?
Correct, Bo. If I move a negative charge in the direction of the electric field, it gains electric potential energy. And class, what happens if I let go of the negative charge now?
It goes upward?
It accelerates upward.
It accelerates opposite the direction of the electric field.
Sure.
Exactly.
Nice.
How?
I love this demo.
You do that?
I do want to point out the negative and the dot product in the equation. As I move the charge in a direction opposite the direction of the electric field, the direction of the displacement of the charge and the direction of the electric field are opposite to one another. Therefore, the angle between those two directions is 180 degrees. The cosine of 180 degrees is -1, which makes the change in potential energy of a positive charge positive, and the change in potential energy of a negative charge negative. In other words, the electric potential energy of a positive charge increases as a positive charge moves opposite the direction of the electric field. And the electric potential energy of a negative charge decreases as it moves opposite the direction of the electric field. Realize, there is no gravitational analogy to negative charge. There is no negative mass. So we are not used to this concept of the change in potential energy depending on whether the charge is positive or negative.
Right. There is no such thing as negative mass.
Next, we need to define electric potential. Just like we define electric field in terms of the force experienced by a small positive test charge, we define electric potential in terms of the energy experienced by a small positive test charge. Electric potential equals electric potential energy divided by charge. The units for electric potential are joules per coulomb or volts. The symbol for volts is a capital V.
But,
I know, the symbol for electric potential is a capital V, which is the same as the symbol for the units for electric potential, volts. This is not my fault. I don't know whom to blame. However, it is definitely not me.
Grumble.
Grumble.
Grumble, grumble.
Grumble, grumble.
Electric potential is a scalar attribute of a vector electric field. In other words, the electric potential does not have direction. This fact that electric potential is a scalar can be very helpful in this class. I'll actually demonstrate that later in this lesson. Now, most often we are interested in the electric potential difference, not just electric potential. Electric potential difference is the difference in the electric potential between 2 points.
Yeah.
It could be called change in electric potential, but we call it electric potential difference.
Yep.
Actually, electric potential difference is better because it is a difference in the electric potential values at each location, regardless of whether a charge actually moves through that difference or not. So nothing has to go through a change in electric potential. The electric potential difference is just always there.
That actually makes sense.
Yeah, sure.
Thanks.
Right. Electric potential difference equals electric potential final minus electric potential initial. Often points A and B are used instead of initial and final. That means electric potential difference equals change in electric potential energy divided by charge. We can substitute the dot product integral equation in for change in electric potential energy, and the charge cancels out. And we are left with electric potential difference equals the negative of the integral from point A to point B of the dot product of the electric field and the infinitesimally small displacement dr. We will often set the initial electric potential or electric potential at point A equal to 0. Notice we can now essentially go in the opposite direction than we did at the very beginning of this lesson. We can go from the integral to the derivative, and we get that the electric field in the direction of r equals the negative of the derivative of electric potential with respect to r. Okay, now that we have the electric potential units of volts, let's take another look at the units for the electric field. Bo, what are the units for the electric field?
Well, electric field equals electrostatic force over charge, so the units are newtons per coulomb.
And what if we multiply that by meters over meters, which we can do because meters over meters equals 1, and you can multiply any number by 1.
On the top, we then have Newton meters, and Newton meters are joules, and joules per coulomb are volts. So the units for electric field are either newtons per coulomb or volts per meter. They are the same thing.
Exactly, Bo. Thanks. All right, more stuff. If a charge is moved from point A to point B via an external force, the external force does work on the charge, which changes the electric potential energy of the charge. And as long as there is no change in the kinetic energy of the charge, that work equals the charge of the charge multiplied by the electric potential difference the charge experienced. Next, let's talk about a unit of energy which is often used for very small amounts of energies, like one would use in atomic and nuclear physics. It is the electron volt, or EV. An electron volt is defined as the energy a charged field system gains or loses when a charge of magnitude lowercase e, the elementary charge, or the magnitude of the charge on an electron or proton, is moved through a potential difference of 1 volt. Bobby, please determine the magnitude of the work done on a proton as it goes through an electric potential difference of 1 volt.
We know work equals charge times electric potential difference. The charge on a proton equals 1.6 times 10 to the negative 19 coulombs. And the electric potential difference is 1 volt. So 1.6 times 10 to the negative 19 coulomb volt.
And what is a coulomb volt?
Well, a volt is a joule per coulomb. So coulombs cancel out and the units are joules. Right, it is energy. It is in joules. So 1 electron volt equals 1.6 times 10 to the negative 19 joules.
Great. Now, I do consider the term electron volt to be a misnomer, because electron volt sounds like a unit of electric potential because it has the word volt in it. However, the electron volt is a unit of energy. Please be careful of that. Also, the electron volt is a unit for a positive amount of energy, even though the electron is negative. Now, let's say we have 2 large charged plates of equal magnitude. The top plate has a positive charge and the bottom plate has a negative charge. In a previous lesson, we showed that the electric field between parallel plates is uniform and is directed from the positive plate to the negative plate, which is, in this example, directed downward. Let's say the electric potential difference between the 2 plates is 12 volts, and the distance between the 2 plates is 1.0 centimeters. Let's define the top plate as plate A and the bottom plate as plate B. Let's start by determining the general equation for the electric potential difference when going straight across from plate A to plate B. Billy, please do that.
Absolutely. Well, we already determined the electric potential difference equation in terms of the dot product, or using cosine theta. Let's use the one with cosine theta in it, because we are determining the electric potential difference from plate A to plate B. The direction of dr is the same as the direction of the electric field, and the angle between those 2 directions is 0 degrees. The cosine of 0 degrees is 1, and actually the electric field is constant from plate A to plate B, so we can take that out from under the integral. And the integral from plate A to plate B with respect to position is the distance between the 2 plates, which we have labeled d. That means the equation for the electric potential difference in the direction of a uniform electric field equals the negative of the electric field times the linear distance between the 2 points.
Thank you, Billy. This is a good time to discuss the negative in the electric potential equation. The negative means the electric field points in the direction of decreasing potential. In other words, a charge moving in the direction of the electric field will go through a negative potential difference, and a charge moving opposite the direction of the electric field will go through a positive electric potential difference. All right, let's add more to the problem. If we release a proton from the inside surface of plate A, what will the speed of the proton be right before it runs into plate B? Bo, please solve this problem.
Sure. We can draw a free body diagram of the forces acting on the proton, sum the forces, solve for acceleration, and then use the uniformly accelerated motion equations to solve for the final speed of the proton. So, in the free body diagram...
Actually, Bo, you could certainly solve this problem that way. However, let's not solve it that way today. Could you instead use conservation of mechanical energy, please?
Okay. But how do we know mechanical energy is conserved in this example?
There is no work done on the proton by a force applied or by a force of friction, so mechanical energy is conserved.
So, mechanical energy initial equals mechanical energy final. Actually, let's do mechanical energy at plate A equals mechanical energy at plate B instead, because we already have those defined. At plate A, the proton has electric potential energy. However, it does not have kinetic energy because it starts at rest. And there's no spring, so no elastic potential energy. And gravitational potential energy. Does the proton have gravitational potential energy?
That is a good question. The gravitational potential energy for subatomic particles is usually negligible, and it is in this situation. You could prove it by comparing the change in gravitational potential energy of the proton to the change in electric potential energy of the proton. However, we're not going to take the time to do that today. So typically for subatomic particles, gravitational potential energy is negligible, and you do not need to identify a horizontal zero line.
Sure. So the only type of mechanical energy the proton has at plate A is electric potential energy. At plate B, the proton has kinetic energy and electric potential energy. Subtract electric potential energy at A and kinetic energy at B from the whole equation. On the right-hand side, that equals the change in electric potential energy. We know electric potential difference equals change in electric potential energy over charge. That means change in electric potential energy equals charge times electric potential difference. Now we have negative 1/2 times mass times speed at B squared equals charge times electric potential difference. We can solve that equation for the speed of the proton at plate B, but we cannot take the square root of a negative number. As a proton moves in the direction of an electric field, it loses electric potential energy.
That means the electric potential difference in the direction of the electric field is negative.
Oh, yeah. I think I forgot that.
Yes, and sadly it is often forgotten. Bo, please substitute in numbers.
The charge on a proton is positive 1.6 times 10 to the negative 19 coulombs. The electric potential difference from plate A to plate B is negative 12 volts. And the mass of a proton is...
On the AP Physics C table of information, which we will get during the exam, it says that the mass of a proton equals 1.67 times 10 to the negative 27 kilograms.
And we get 47,952 meters per second, or 48 kilometers per second with 2 sig figs.
Whoa, that seems really fast. How fast is that?
Multiply by 3,600 seconds over 1 hour and 1 mile over 1,609 meters, and we get 107,288, or 1.1 times 10 to the 5th miles per hour.
Yeah.
That is fast.
Yeah.
Yes, it is. Now let's look at determining the electric potential difference when moving at an angle relative to a uniform electric field. So let's remove the charged plates from our illustration and retain the uniform electric field. Let's define points lowercase a1 and lowercase b such that we have the same electric potential difference from point A1 to point B as we did before. Negative electric field times distance d. Let's define point lowercase a2 such that it is at a horizontal distance x from point A1, and let's label the distance from point A2 to B lowercase h. And Bobby, please determine the electric potential difference when going from point A2 to point B.
The electric potential difference from point A2 to point B equals, well, we have both the dot product equation and the one with the cosine theta in it. Let's use the one with the cosine theta. Theta is defined as the angle between the direction of the electric field and the direction of the infinitesimally small displacement dr, which is directed from A2 to B.
That angle and the angle in the triangle by point B are alternate interior angles, so they have the same value.
Right. Cool. Cosine of an angle equals the length of the adjacent side over the length of the hypotenuse. Therefore, the cosine of this angle equals length d over length h. The electric fields, distance d, and distance h are all constant values, so they can all be taken out from the integral. The integral from a2 to b with respect to position is just the distance from a2 to b, which is the distance h. H cancels out, and the electric potential difference between point A2 and point B equals the negative of the electric field times distance d.
That is the same as the electric potential difference from point A1 to point B. Why is that?
That is because the electric potential difference from point A2 to point A1 equals 0. The angle between the electric field and the infinitesimal displacement dr, which points from A2 to A1, is 90 degrees, and the cosine of 90 degrees equals 0.
In other words, points A1 and A2 have the same electric potential. Points A1 and A2 are on an equipotential surface. In fact, we just showed that every point along the line created by points A1 and A2 have the same electric potential. That makes that an equipotential line. If we are talking about a surface with the same electric potential, it would be an equipotential surface. An equipotential surface or line has the same electric potential at every point on the surface or line. Equipotential surfaces or lines are always perpendicular to the electric field. That means the electric field has no components along an equipotential surface or line. Actually, I'm going to stop saying both surface and line. You get the idea. Equipotential lines are sometimes called isolines. The work required to move a charge equals charge times electric potential difference, and when moving a charge along an equipotential surface, the electric potential difference is 0. Therefore, the work required to move a charge along an equipotential surface is 0. Let's switch our example now to a positive point charge. In a previous lesson, we determined the electric field. It looks like this. Given what we know about equipotential lines, we know the equipotential lines around a positive point charge look like this. Actually, let's make all of those equipotential lines blue because that is what we did last time for the electric field for a positive charge. Notice how all the equipotential lines are perpendicular to the electric field lines. And let's switch to a negative charge in red. Now, I know the electric potential lines for the negative charge look like they are identical to the ones for a positive charge. They are not identical, only very similar. The electric potential lines for the positive charge all have positive values. However, the electric potential lines for the negative charge all have negative values. So, same shape, but the positive charge has positive equipotential lines, and the negative charge has negative equipotential lines.
Positive equipotential lines around a positive point charge and negative electric potential lines around a negative point charge. Yeah.
Right. Now let's switch to a simple electric dipole. An electric dipole is a pair of electric charges of equal magnitude but opposite sign, separated by some typically small distance. I probably should have mentioned that last time, but, I can't think of everything.
You do come pretty close, though.
Thanks, Billy. Let's start with just the electric fields caused by each of the singular charges. And let's add the equipotential lines caused by each of the singular charges. And let's transition to the electric field and equipotential lines caused by both charges together. The electric dipole. Actually, let's do that again. Start with just the electric fields caused by each of the singular charges. Add the equipotential lines caused by each of the singular charges. And again, transition to the electric field and equipotential lines caused by the electric dipole. Now, notice the electric potential caused by the electric dipole is calculated simply by summing the values of the electric potential caused by each point charge. This is because electric potential is a scalar value. This means there exists, for an electric dipole, a vertical equipotential line directly between the two equal magnitude charges because the electric potential from both charges adds up to 0 along that line. That means all of the equipotential lines in the positive point charge half of the electric field are positive, and all of the equipotential lines in the negative point charge half of the field are negative. Actually, we have yet to discuss the equation for the electric potential caused by a single point charge. So let's get the electric potential and field line map back on the screen around just the singular positive point charge. The equation for the electric potential which surrounds and is caused by a point charge equals the Coulomb constant times the charge, all divided by the distance from the center of the point charge to the location of the electric potential. This equation defines zero potential to be infinitely far away from the point charge, just like the universal gravitational potential energy equation. Bo, using that, could you please determine the electric potential energy of two point charges?
We know electric potential equals electric potential energy divided by charge. Electric potential energy then equals charge times electric potential. Substitute the equation for the electric potential of 1 point charge, and we get that the electric potential energy of 2 point charges equals the Coulomb constant times charge 1 times charge 2, all divided by r, the distance between centers of charge of the two charges.
Thank you, Bo. Realize, because electric potential and electric potential energy are scalar values, determining those values for multiple particles uses superposition. You just add all the values together. Now, in order to understand how useful it is that electric potential is a scalar and not a vector, let's revisit an example from a previous lesson. Let's determine the electric potential caused by a uniformly charged thin ring of charge positive q with radius lowercase a at point P, which is located on the axis of the ring, a distance lowercase x from the center of the ring. Bobby, please determine that electric potential.
Electric potential from a point charge equals the Coulomb constant times charge divided by r, the distance from the center of the point charge to the location of the electric potential. But this is not a point charge. It is a continuous charge distribution. So we need to break the uniformly charged thin ring of charge positive q into an infinite number of infinitesimally small charges dq. That means the electric potential caused by a continuous charge distribution equals the integral of the Coulomb constant over r with respect to charge. The Coulomb constant and r are constant for every charge dq, therefore they can come out from under the integral. The integral of dq is just q, the charge in the ring, but r is not one of our known values, so the Pythagorean theorem tells us we can replace r with the square root of the quantity a squared plus x squared, and we have the electric potential at point P caused by the uniformly charged thin ring.
Very nice, Bobby. Billy, can you use the electric potential at point P to determine the electric field at point P?
Of course I can, Mr. P. But how are electric field and electric potential related?
Earlier today, we showed that the electric field in the r direction equals the negative of the derivative of electric potential with respect to the r direction.
Right. Thanks, Bill.
Yeah.
We can substitute in the electric potential at point P, Bobby just derived, and change it to the x direction because we know the electric field at point P is in the positive x direction. We showed that last time. The Coulomb constant and charge are constant for every value of x, so those can come out from the derivative. And 1 over the square root is the same as an exponent of negative 1/2. We need to use the chain rule to take this derivative. So the derivative of a squared plus x squared to the negative 1/2 power with respect to x equals negative 1/2 times the quantity a squared plus x squared to the negative 3/2 power. And the derivative of the quantity a squared plus x squared with respect to x equals 2x. So the electric field at point P equals the quantity Coulomb constant times charge of the thin ring times the variable distance x, all divided by the quantity a squared plus x squared to the 3/2 power.
Hold up. Why could we take r out of the integral, but x had to stay in the derivative? I mean, how can x not be constant and yet r is constant? It all depends on what you are taking the integral or derivative with respect to. the integral is being taken with respect to the charges on the ring, dq, and every charge dq on the ring is the same distance r from point P. However, the derivative is being taken with respect to position in the x direction. In other words, x is a variable distance along the x-axis for the derivative.
Thanks.
You're welcome.
Thank you, everybody. Notice that this derivation of the electric field at point P is much easier than deriving the electric field directly like we did in a previous lesson. Therefore, I would recommend you remember that for a continuous charge distribution, you can first determine the electric potential and then the electric field, and that is often easier than solving for the electric field directly. That concludes my review of electric potential for AP Physics C, Electricity and Magnetism. Next time, we are going to review conductors in electrostatic equilibrium. Thank you very much for learning with me today. I enjoy learning with you.